now going to work on calculating the bias point for a transistor, a NPN or PNP bipolar transistor. So the first thing that we note is that when we have a bipolar transistor, we have current flowing in the collector, from the collector through towards the emitter. We have a base current that flows from the base towards the emitter, and finally we have an emitter current. Now we know that the emitter current is equal to the sum of the base current plus the collector current, just by writing KCL at the emitter node. Now when we talk about the bias point, we typically draw a set of characteristic curves for the transistor that are defined as the collector current, IC, versus the collector to emitter voltage, VCE. And of course, if you've seen these curves before, they look something like this. For different VBEs, we get a family of curves. We can represent cutoff, where we know zero current flows at the zero current point. We know that saturation for a bipolar transistor always occurs for approximately 0.2 volts. This is called VCE sat. So once our collector to emitter voltage gets above approximately 0.2 volts, the device goes into the forward active region. So when it's below 0.2 volts, this region is called saturation. When it's above 0.2 volts, we have forward active. We're always going to try and set what we call a Q point somewhere in the forward active region. So this is our Q, or bias point. And there's a corresponding VCE Q and a corresponding IC Q for this particular point. We're going to try and set our device into the forward active region to have some collector current in this region and some collector to emitter voltage in this region. Now with a bipolar device, what we do first is assume the device is in the forward active region, or the FAR. Then we're going to use KVL and KCL to check if current is flowing. If our assumption fails and current isn't flowing, then the device is not in the forward active region and we need to increase the base to emitter voltage. After we've made sure the current's flowing, we need to find VCE and check to see if VCE is greater than our 0.2 volts. And if both of those conditions are true, then the device is in the FAR. Now once the device is in the forward active region, we need to find a way to calculate what the small signal or the AC gain of the circuit is. So the way we're going to do this is we're first going to assume that we've managed to put a sufficiently high enough VBE into our device, and that we also have placed a sufficiently high enough VCE greater than 0.2 volts across the device. And if we were to plot a curve of our collector current, this time versus VBE, we would see that the device would be off, zero current flowing, until we reached a diode drop of approximately 0.7 volts for the transistor, and then the current would start to increase exponentially. We know that our collector current relationship is IC is equal to ISE to the VBE divided by VT, our thermal voltage. Our Q point sets the DC level of the VBE voltage and IC current, and our small amplitude swing is going to occur around this Q point. We're going to make the assumption that the amplitude of the signal does not cause the transistor to leave this bias point in a significant way. In other words, we're going to make a linear approximation. So ultimately what we're saying here is that we have a small swing in VBE and IC. The transistor effectively just converts voltage to current. So the transistor converts a voltage difference between the base and emitter, or VBE, or we'll say a delta VBE, into a delta current, or delta IC. And so we can define the delta in current with respect to the delta in VBE as a parameter G sub m, and ultimately, if we take the derivative of our expression for current, we would find that Gm is equal to IC over Vt. So what we see that's interesting here is that the transconductance, or the ratio of how well the device converts voltage to current, is only dependent upon the DC current and the thermal voltage, which only depends on temperature. So recall our transconductance is how well we convert voltage to current. So our transistor is always converting a voltage to a current, and what we need is an output resistance to convert the current flowing through a resistor back to a voltage. We're first going to look at a couple of other small signal parameters, but our first small signal parameter is the transconductance. In the next part of the lesson, we will look at resistances associated with the transistor, and we've already seen capacitances associated with the transistor.